it's not as positive, so it's not pulling the electron density to the oxygen as much, so it would just stay as being partially negative, and this OH bond isn't being as depolarized. But Fe3 plus is so positive, it's pulling the electron density close towards the Fe3 plus, and what's happening here is now the electron density is being pulled away from the oxygen, and it's close towards the Fe3 plus. So now this oxygen atom is more partially positive than it is partially negative, and that now depolarizes this bond, because this hydrogen is already partially positive, the oxygen is now partially positive. This bond becomes more unstable. It wants to repel, because obviously like terms repel, opposites attract. So this is now partially positive. The electrons that would have been here are now going to favor the hydrogen. It wants to leave. It doesn't like being in a position where they're repelling each other so much. So the oxygen is going to be more favored in this case here. So the electrons are going to it needs to form some sort of leaving group. So the electrons that would have been here are now falling back to the oxygen, right? Yep. And now this acts as a leaving group. So now you have this bond is now broken, right? And you formed a H plus in solution. Yep. And that bond would have just been now an OH minus bond. This is more now it's more negative now. It's got a but again, you don't need to worry. That's a terrible cloud. Again, you don't need to worry too much about I'm just explaining this so you understand why it's happening. I think you do need to know, you do need to know why this happens. I'll explain it more in depth in another video. I think I've pretty much explained it in depth anyway, to be honest. I think that's pretty much mostly in depth anyway. I ended up going in too much depth anyway. But yeah, that's what's happening here. That's why, but as I said, it's releasing a proton. And if you release a proton, that's what a Bronsted-Lowry acid is, a proton donor. So this has just donated the proton, and now you no longer have, Fe3 iron-free hexaaqua. You have Fe H2O5 OH minus, and you've released the proton in solution. So this is now an acidic solution, and this is less likely to happen with an Fe2 plus, because Fe2 plus hasn't got as much of a high charge density. Fe3 plus has a high charge density and is more positively charged, and is more likely to induce this effect, whereas Fe2 plus hasn't got as much of a higher charge density. It wouldn't cause this much of an effect. Again, that's more of there is a topic on this that I'll do in a later video if I ever end up going to a video. So I've just explained it there. Right, so the last part of this now is spectroscopy, right? I remember what I need to do now. So, yes, I remember what I realized I was missing something. One last thing here. So, specific complex colors. There are specific complex colors. Right? So one is Fe2 hexaaqua. Oh. And that's pale green. These are the ones that most commonly come up, but you should know all of them. Vanadium 2 hexaaqua. Again, this is just in solution. That's why you see it as vanadium 2 hexaaqua is a violet color. So violet, yes, I got those two mixed round. Vanadium 2 hexaaqua. ultraviolet. You should write the state symbol. Aqueous. Free. I'm not gonna go through every single version of them here. Actually, you know what? Let's see if you're paying attention. Vanadium. Yeah, vanadium hexaaqua, vanadium 3 hexaaqua. Oh, what color? What color would it be? I did mention it. Let's see if you're paying attention. And copper. This one I think is pretty much obvious. But let's see if you can get this one as well. Now you should know that this one is green. And this one is a deep blue. Now, last one here. I promise we're getting towards the end of this video. I promise that. Spectroscopy, right? So you can use the color of ions to find their concentrations, and this uses a technique called spectroscopy. Principles of spectroscopy. You can shine white light through a colored filter to remove everything but that color of light, and you can then let this light fall on a sample of transition metal solution. The more light it absorbs, the higher the concentration of the solution, and we can compare the amount of light absorbed to a calibration curve. And just let me explain what's going on here, because I know you're probably thinking, what the fuck is he talking about? He's put way too many words into my head, and I'm losing it. Right, so there's a way that we can actually the absorbance of light, if we can actually use this information here to create a graph, right? What we're trying to do is we're trying to create this really good graph. I'll show you the graph later on here, right? This is graph, right? But we need to create this graph because, as you can see, this is a very nice, neat graph, and it's very directly proportional, and we can use it, right? And we can use that information from that. We can use that graph to help us work out the unknown concentration of a sample using the absorbance of light. Now, how do you do this, right? So we know that white light is built up of all the different wavelengths of light in the visible light spectrum, right? So, as I said before, when it comes down to the energy gap here, right? We're absorbing generally one specific wavelength of light, so, that sample absorbs, right? So just to ease in this process, what we do is that we shine white light through a colored filter, and the filter that we want. So let's say our sample is copper 2 hexaaqua, right? Or copper 2 plus, right? We know that I just know that one off the top of my head, that absorbs yellow light. So what you use in that example is that you use the yellow light filter to remove everything but that color of light, and you can then let the light fall onto a sample. So I'll show you a diagram below to make it a bit easier. Actually, I'll show you here, right? So this is the white light, and let's use a yellow sample here, right? Oh, I'm not gonna color it in too much detail, but so it's just you get the idea, right? It's a yellow filter. I'm not gonna do it properly, like, yeah, but you get the idea, right? Yellow filter. White light source. Filter. Sample. And a detector. Right? So this is our white light that's made up of all the different specific wavelengths of light. This is a filter. It can be any filter, but it's the filter that's used to focus that specific wavelength of light. Because remember, a filter is able to reflect back any other wavelength of light and only allow that specific wavelength of light to go through. And this just helps us focus on that specific wavelength, because that's the wavelength that's going to get absorbed anyway, right? So that wavelength, I'm going to use the yellow color here. That will then pass then to the sample, right? And then the sample will absorb that light. And then what we're measuring here, what this detector is measuring is how much of that light is being absorbed by the sample, right? Because the more concentrated the sample is, if there's more of that sample, there's more light going to be absorbed. If there's less of that sample, there's going to be less of that light being absorbed, because there's less of the compound to absorb that light. It's directly proportional. The more of your sample in your solution, because that's what concentration is, right? It's the amount of your substance in a solution, or in a volume of space, right? The more concentrated your solution is, the higher the absorbance of light, because there's more of that compound to absorb that light. So that's, and because we know that, now that we know that information, we can use, because we know it is directly proportional, we can use that to create a graph, and then we can use that graph to help us work out any unknown concentrations of samples that we may have if we were trying to work out the concentration directly. If we didn't want to do a long process of spectroscopy, other spectroscopy methods, and yeah. So where was I before? Yeah, so then we can compare. So yeah, I've pretty much have done that. Yeah, so now the calibration curve. So we've done now, this is the method that we're doing now, and we've collected the data. So when doing the spectroscopy, we can't calculate the concentration of a sample without comparing it to known concentrations. We first measure the absorbance of solutions whose concentrations we know, and then we plot these on a graph. This graph is called the calibration curve, and I'll show you an example below. And we then use the absorbances of the unknown sample to interpolate the graph we've created to work out what the concentration is. Now I'll explain what that is. Give me one quick second. Sorry, need that. So I'm gonna break this down what it says here, because I know there's a lot of words that maybe again you don't understand. If you understand everything that's going on, you can just move straight on, because I don't want to slow you down. I'm just putting it here in case you listening and you don't get what I'm saying here. So in order to create this calibration curve, we need to have some sort of comparison. So what we're doing here to create this curve, right? So this is the curve. It's not really a curve. It's directly proportional graph, but we call it a curve. But you should use a ruler to create this graph, right? What we would use is that we'd get the known. So we're getting a sample. We know what the sample is. We just don't know what the concentration of it is. So we get the sample, but we get varying concentrations of our sample in order to create a curve. So let's say, again, I'm going to use the example of copper 2 sulfate. So let's say we had an unknown sample of copper 2 sulfate. What I would do to create a calibration curve is that I would get varying concentrations of copper 2 sulfate, 0.5. It could be even, it depends on how much of samples you have. In a proper science lab, they would have many samples to get as accurate curve as possible. But if you're going roughly, you can go 0.5, 1, 1.5, and it should be a lot more accurate than that. You should be going 0.25, 0.5, 0.75, 1, 1.25, 1.5. You get the one I'm trying to get here, up until 2 or 2.5, right? Now, once you have that information, once you get those samples, you then measure the absorbance of light of each of those samples. Now, this is a really weird graph. It could be a moles per dm cube. This is a really weird one. I use it from Google Images and I try to emulate it. But you could use 0.5 here, 1.5 moles per dm cubed, right? And you can use absorbance in ABS, or you can use percentage absorbance, because it depends on the settings that you use on the machine. This is a required practical that you have to do for I think you do it in biology actually, if I'm not being mistaken. I'm not sure if it's a required practical in chemistry, but it's definitely required practical in biology, right? It can use percentage absorbance, so you can go from 0, 10, 20, 50, 100%, right? I prefer using the percentage and moles per dm cubed, right? So let's just go for that, right? It's pretty a lot better. So 100%, 50%, 75%. This is probably too confusing, right? Probably shouldn't have done that, but yeah, you can see the absorbance of light as a percentage. So if it's 50% absorbance, it means that out of all of the light that's being absorbed, only 50% of the light is being so out of all the light that was shone, only 50% of that shone light has been absorbed by the sample, as according to the detector. The detector has shown that 50% of the light has been absorbed, right? And if 75% of the light has been absorbed, it means the detector has only recorded 25%. That's how this whole thing works, right? If you think about it, if this detector is only detecting 25% of light out of this white light, it means that 75% of it is being absorbed, right? Just that's pretty much how it is, right? So that's pretty much what you're doing. So you repeat this process. You basically replace this. This is actually, we call this little tube thing a cuvette. We fill it in with our sample and we put it into the machine. And then obviously we're just changing the concentration of the solution, and we repeat this process every single time, and we record the data in a table of values. Remember, some sort of table like this will be concentration on this side in moles per dm cubed, and the absorbance of light as percentage absorbance, whatever. And record the light for each of the concentrations, so and so, 0.25, 0.5, 0.75, whatever, and we'd measure the absorbance. And what you should see is that it's more or less directly proportional, and then you should be able to fit a line of best fit, so on and so on. Now, why is this all that? Why have you done all of this, right? Again, this could be a 6-mark question in the exam, or 5-mark question where they tell you to get all of this information done. They may ask you to explain this, and then they may ask you to then draw this part out, right? That's why I'm explaining it in so much, every single part, so you understand every single part, right? And then why is this important? Because now that we have this graph, we can be, based off of the data that we've seen, it's very clear that there's this kind of trend here. We can assume direct proportion. We can make that assumption that it's directly proportional. In theory, it's not technically 100% proportional, but based off of this, we can make that assumption because it's so close. And I think if you were able to do a statistical test, you could probably test that it's okay to make that type of level of assumption. But I'm not going to get too much into that. You don't have to know too much about that. Now, I said here about this interpolation part. I think everything I've explained is this part here, right? Now I've explained that. Now I'm going to explain this. I promise I'm coming to the end of this video. I know it's a very long video, and there's probably no one listening at this point, but I tried, right? So I said we then use the absorbance of the unknown sample to interpolate the graph we've created to work out what the concentration is, right? So what's interpolation? I'll show you what interpolation is, right? So extrapolation, if you know what extrapolation is from maths, right? So extrapolation is, say your graph is like that, right? And they tell you to extrapolate the graph. It means you just continue on. You make the assumption that the graph will continue as this ongoing trajectory, and it will continue on like that. That's what it means to extrapolate a graph, continuing on the graph. It could apply for a exponential. If it's like this, you can assume it's going to be like that, so on and so on. Interpolating a graph, it means that you're intersecting the graph at a specific point, right? So it means that if I wanted to know what the absorbance is at 0.5, say this was 0.5, actually 0.5 would be probably more like, if this is 2, then 0.5 is more like here, right? What I would do, if I want to know the absorbance or the percentage absorbance, I'd go up from this part here and I'd go across here. That's what it means to interpolate a graph. You do it a lot more, but you probably didn't know what it meant. But that's what interpolation is. It's just intersecting the graph at a particular point, right? Inside. So this, and it's the same thing here. So now, and you can do it either way. It doesn't have to be from X to Y, it could be from Y to X. And in this case, it will be from Y to X, right? So we've done this now, and we've done our known samples. Now we repeat this process, but now we would add the unknown concentration of the sample of the unknown concentration. Now we know this is copper sulfate, but we don't know what the concentration is. We have our calibration curve. What's going on now is that we're shone the light through the sample. We're just repeating the process, but now we're trying to measure the absorbance of light from this sample. Why is that information useful? Because now if we know the percentage of absorbance is 50% or 1, whichever method, whichever setting that you're using, I'm going to take away this part because it's probably a bit more, let's just do it as percentage absorbance, because it's probably, you can use the ABS part, it's not confusing, it's just the setting that you use. 25 percentage. 25, 50, 75, and then 100, right? Good. Done. Right? So let's say from our sample, we don't know what the concentration is, but the percentage absorbance was 63%, which is like probably roughly like here, right? And you'd get your ruler. Have my ruler here. And I don't like this. I'm not going to use micrograms per milliliter. I'll use moles per dm cubed again, because 0.5, 1, 1.5, moles per dm cubed. Right, sorry. I just didn't like the way it was. But let's say it was 63.5, right? So let's say we done the absorbance, and from this data that we've collected from the colorimeter, again, this whole the machine that we're using is called a colorimeter. I should have made that obvious from before, but the machine that we're using for this process is called a colorimeter for colorimetry. We get our ruler, we then interpolate this graph. We found out that it has absorbance of 63.5. Just call that 63.5%, right? And we scale downwards. And then from this graph here, now you'd use lined paper, or not lined, square paper, and it should be giving help you out a bit more. But from here you can see it's probably 1.2. So now we know that the sample that we have has a concentration, the unknown concentration of our sample. After doing this colorimetry, we know that its concentration is 1.2 moles per dm cubed. We can make that assumption, and that's it. We've worked out what the unknown concentration is, and that's all it is. Hopefully you understood that. If you didn't understand that, let me know. That is essentially what is going on here. So from this video, we've basically done, we know that with metals with the energy gap, I'm going to just change back. Metal with energy gap absorbs light of a particular energy. So absorbs light of energy equal to the energy gap, difference in energy. And of course, we don't see the absorbed light. We should know that from GCSE, that you don't see absorbed light, only the light that gets emitted or reflected back to you. and it reflects all other energies of light. Energies of light, wavelengths of light, frequencies of light. I'm going to say frequencies is more of a probably a better term, because that's what the energy is in the form of. It's in the form of frequencies of light. So it reflects all other frequencies of light. And we see this we see this reflected light. Great. And just to summarize the features of spectroscopy, white light shines through a colored filter to remove everything but that color of light. And then this light then falls onto a transition metal sample solution. The more light it absorbs, the higher the concentration of the solution, right? And that is pretty much it. The last thing here is going to clarify again the D subshell splitting. D subshell splitting, of course, is in a metal. If there's no ligands present, again, actually, that's probably one of the best things. The most important things. I can't get my words out. Most important things you need to understand about this is that none of this would happen if there's no ligands present. You wouldn't see any of these properties. So these transition metal ions wouldn't show these properties if ligands weren't present. Because if there's no ligands present, it means there'll be no D subshell splitting. So they'll just appear as they are white or they all appear to be the same kind of color. So because there's no D subshell splitting. However, when ligands are present, there is D subshell splitting. I'm sorry, I'm getting a bit tired of this video. Sorry. Yeah, this is quite a jam-packed video, and I generally don't like making these videos because of the amount of explanation it requires. I probably would consider splitting this video into two, but apart from that, that's the end of this video, and thank you for listening.